Okay, class. So I have spent some time grading your homeworks and your reflection homeworks and reading your journals for um, week one of forces. And I want to address a couple things that are rather important that everybody um, messed up on, honestly, failed on. Failed is a little high there. I want to say that could have been significantly better. And that's the concept of free body diagrams, F-net equations, and how to go about showing your work on how to solve a problem. So I specifically want to address, I'm going to do this by showing you the boxes question from the homework. And I want to show you what the expectations are for this class and what for grading, for physics in general, for showing your work, and again, explaining what's happening using what's on the paper. So this question had three boxes. One, two, three, and then another rope here. And you were told that this force out here, and of course my pen doesn't want to work, this force out here was 60 newtons. And you were told that each box had a mass, mass of box 1, mass of box 2, and mass of box 3 were all 5 kilos. Okay, so box 1, box 2, box 3 is what I'm going to call them. Okay, and you were asked to determine and show what the tension in the ropes in between the boxes are. So I'm going to call this rope 2 and I'm going to call this rope 1. Call it whatever you want, but that's what I'm going to choose to do. Now, there were many ways to go about this problem, but a lot of you just kind of made assumptions and came up with answers. Now, those answers may have been correct, but again, physics is not about getting the right answer. It's about showing your work to the right answer. Okay, how did you get your answer? That's the important part in this class is how did you get your answer? Okay, and so I want to show you the steps for going about this problem. And these are the steps I'm going to be looking for throughout the semester. It's showing your work from beginning to end. So in a force question like this, the big things are free body diagrams, also sometimes called force diagrams, and F-net equations. Okay, both things are addressed in the chapter, so I know you guys read about them, but this is something that almost nobody did on this question or any of the other questions. So again, these are important. These are the two most important things you can learn, in my opinion, all semester long. How to draw a good free body diagram and how to set up an F-net equation based on that free body diagram. So what we've got here is we've got three objects, object 1, object 2, object 3. What I'm going to do is I'm going to put a dot on each one of them. And what I'm going to do is I'm going to label all the forces that are acting on each of the objects. So object 1 has got a normal force going up. We'll call that Fn1. And it's got gravity going down, Fg1. And it's got this rope pulling to the right. We're going to call that Ft1. Okay, box 2 has an Fn2 going up, an Fg2 going down, an Ft2, tension from rope 2, pulling to the right, and it has an Ft1 going backwards because it has tension from this rope pulling it backwards. And these two forces, we call them the same thing. They are equal and opposite. This is a Newton's third law relationship. Box 1 pulls on box 2, box 2 pulls on box 1 with an equal and opposite force. And for box 3, we've got an Fn3, an Fg3. This force, which we just called F, and then back here, an Ft2, which again, these two forces are equal and opposite. Newton's third law. Okay, so there is a free body diagram for each object. Okay, now what I'm going to do is I'm going to now, so I've done free body diagram. Now I'm going to do an F-net equation, but I'm going to do it for each object. Now, first things first, we could set up F-net equations in the y direction, but for this question, there was nothing happening in the y direction. The boxes weren't going up or down, and so I'm not going to worry about my F-net equations for the y direction. So what I'm going to do is I'm going to look at box 1, which, if I can get my pen to work, there we go. Box 1. Box 1, we've got an F-net x is equal to the mass of box 1 times the acceleration of box 1, and that's going to equal ft1. Now, technically, the only thing I know right now is m1. So this is 5 times a1 is equal to ft1. And that's technically all I know at this point. Box 2, again an F-net x, is going to equal mass of box 2 times the acceleration of box 2. And if I look at box 2, I have equals, I've got an ft2 going to the right minus an ft1 going to the left. So what I've got here is I've got 5 times a2 equals ft2 minus ft1. Well, I don't know either. I don't know anything else except what I do know from over here is that ft1 equals 5 times a1. So I could and will substitute this in. And so what I have now is I have ft2 minus 5 times a1. Again, that's where I've got to stop. And now what I'm going to do is I'm going to look at box 3. Box 3, F-net x, is equal to m3 times the acceleration that it experiences is equal to f, it goes to the right, minus ft2. Again, I've got 5 times a3 is equal to 60 minus ft2. Well, if I go up here, I can solve for ft2. I get that ft2 is equal to, I've got 5a2 plus 5a1s. So I can take this, substitute it into there, and this would give me 60 minus 5a2s minus 5a1s. Now, what we need to do is we need to make a statement. We know that this rope out here is pulling all of these boxes together. So they're all moving along at the same rate. So therefore, since they all move together, at the same rate, A1 has to equal A2 has to equal A3. So we're just going to call that A. Which means if I go back over here, what I now have is I get 5A equals 60 minus 10A. I bring the 10A over to the other side, 15A equals 60, and I get that A equals 4 meters per second squared. Which many of you got, but you just made an assumption with no statement of fact that, oh, 60 has to equal 15A. Well, why is that true? Well, this is why it's true. Because 60 here, this force was pulling on just box 3. Yes, box 3 was hooked to box 2, which was hooked to box 1, but the 60 newtons is only applying to box 3. It didn't apply to all 3, it only applied to box 3. That's what this statement says. So now what I can do is I can take this, I can substitute that acceleration back into here. And I get 20 plus 20 equals 40 newtons equals ft2. And I could take this same A and substitute it into there. And here I get then that FT1 equals 20 newtons. Now, I understand that many of you got these two answers, but you made blanket statements saying, oh, it has to be this and it has to be this. My question is, why is that true? Why was this tension just pulling one box? This one seems kind of easy. Well, it's only pulling, it's only got one box behind it, but this rope is touching two boxes. This rope is touching two boxes. Box 1 and box 2 are both 5. Box 2 and box 3 are both 5. So why don't these two ropes, since they're both attached to boxes that have the same mass, why don't they have the same tension in them? Well, it's because of these reasons. It's because of these F-net equations. They show, they prove what's happening. Yes, I know this is a lot more work than many of you did on this question because, again, you guys made assumptions. You can't make assumptions. You have to show your work. When I see assumptions on papers, well, when I don't see anything, I assume that you either looked it up online or copied it off of somebody else. You got to show your work. I need to see where you got your answer. I need to see your free body diagrams. I need to see your F-net equations. Okay, everybody? Please, this week, next week, in the weeks to come, those F-net equations are very important. If you can draw a free body diagram, you can then correctly set up an F-net equation based on that free body diagram. What you do is you take the forces in a given direction and put it into the F-net. So you'll notice that we took the X stuff and put it into an F-net X. X stuff, F-net X. X direction. We took the stuff that was in the X direction and put it into the equation. If it went to the right, it was positive. If it went to the left, it was negative. Went to the right, it was positive. Left, it was negative. It went to the right, it's positive. It equals the total mass times the total acceleration, the net acceleration of that object. Okay, so in this case it's m1, in this case it's m2, in this case it's m3. Okay, guys, if these boxes had different masses, you wouldn't have been able to have just blanketly done equal ratios, which is what a lot of you did. Oh, it's just got to be equal. It's not necessarily true. If this box were 1 Newton or 1 kilo and this were 10 kilos and this were 20 kilos, it would be those tensions in the rope would be different. Well, not this one because this one was set, but the tension in these ropes would be different. Okay, so don't just assume. Please set up your F-nets. Please set up your free body diagrams. Thank you.